Heads up of where we are. We're starting a new chapter this morning, chapter 5, which is the last of the 4 chapters on heat conduction. We're going to finish about half of that this morning and the rest of it on Monday after our first midterm. This chapter is titled Transient Conduction. So now time becomes one of the variables in our solution. We go back to chapter 2 in general to get the heat diffusion equation in 2 dimensions. We write it here for constant properties with no generation. So this is the heat diffusion equation from chapter 2 with constant properties, no generation. If we could solve this with correct initial and boundary conditions, we would get the temperature as a function of x, y, and time. Now, it can be rather difficult, but luckily there is a possibility we can use a simpler model to get results. This model is called the lumped heat capacity model, abbreviated LHC, lumped heat capacity. Here's what the model says. Take a body initially at a temperature Ti, initial temperature, at time 0 Ti. Let's say it starts out hot, just to talk about something. It starts out hot. We blow a cool fluid over it at T infinity with a convection coefficient on the surface of H. With time, the body starts to cool. Starts out hot, blow cool fluid over it, temperature of the body starts to decline. We're going to assume with this simple model that the temperature does not vary inside the body with x and y, but it only varies with time. So now time is not a function, or temperature is not a function of x, y, and time. Now temperature is only a function of time. We're not going to solve the differential equation now. Instead, we're going to write an energy balance on this object. So go back to chapter 1, the end of chapter 1, energy balance on a control volume. E dot in minus E dot out minus E dot G equal E dot storage. Problem said, no generation. E dot G, 0. I'm looking at the model where the object starts out hot, is going to be cooled by a colder fluid. So nothing comes in. But energy does go out by convection. Okay, there's a convection leaving. What happens then? The body has a change in stored energy. We're taking energy out of the body by the cool fluid blowing over it. Okay, so we can then write down what the convection is and the change in stored energy. So we have convection minus HAS and T minus T infinity. Just to review, chapter 1, convection heat transfer, Newton's law of cooling, equal the time rate of change of stored energy, rho CV dt d time. Capital V is the volume. Rho times the volume is the mass. The mass times C gives me a measure of how much energy the object can store. Mass times C, specific heat. Units of the equation there are in watts, both sides in watts. To simplify matters, we let theta equal T minus T infinity. Put that in the above equation then, well, what happens, of course, is d theta dt is equal to dt dt. because the differential of a constant, T infinity, is 0. Okay. Put that up there. So we have, we'll write it down, d theta over T. Okay, there's our little differential equation. The initial condition is when t equals 0, t equal ti, so theta is equal to ti minus t infinity, and we call that theta I. So when time equals 0, theta equal theta I, a constant. Solve then. Theta over theta I. And we get that solution for temperature of the object as a function of time. Now, just to remind you what theta over theta I is. So theta over theta I is a measure of the temperature. And if we want, then we could plot a curve of theta over theta I from 0 to 1. And this is time. Start at 1. And there's different curves, parametric values. Each particular curve is a different value of the time constant called tau. It's in seconds. It's rho CV over HAS. So if you want, I'll just add this to it. You might want to express this as EXP, it's the simplified form of this then, minus T over tau. Okay. We engineers love the dimensionless stuff, you know. So if you, this is a dimensionless temperature difference ratio. This is dimensionless. T over tau is dimensionless. T's in seconds, tau's in seconds, dimensionless. So we like to express things very simply, and a lot of times that's in dimensionless form. But this is called the time constant tau. Now, let's just, for sake of talking about something, let's just take a copper sphere, 6 centimeters in diameter. I don't know that size, a baseball size. 6 centimeters in diameter. Initially at 300 degrees Fahrenheit. Okay, that's TI. 300. I'm going to blow air over it at 30 degrees Celsius, not Fahrenheit. Let's say 70 degrees Fahrenheit, make it English units. So 300 degrees Fahrenheit, initial, and now T infinity, 30 degrees Fahrenheit. I blow air over it. Of course, the temperature is going to drop with time. How? Exponentially. Okay, yeah, drops with time exponentially. But these three curves, let's say you take that copper sphere and put it in this room on a stand at 300 Fahrenheit. And the air in this room is really still. Nobody's hair is blowing. The air in the room is really still. H is going to be really low. Time constant is going to be really high. This arrow means high time constants, low time constants. The direction of the arrow tells me increasing time constant curves this way. So, copper sphere in this room, it cools real slow. Now I put a floor fan in front of it. Turn the floor fan on. Woo, the air blows by it really fast. H becomes really big. H, really big. Time constant, really small. Oh boy, the temperature drops really fast in that copper sphere. So that's the story this graph is trying to tell you. You can say, well, what if the density is bigger? What if the surface area is smaller? You can play the same game with all these variables. So there is the temperature variation with time. Very simple, because it's the simplest possible model that we can use in transient studies. But now we say, yeah, but when can we use it? Okay, well, when we can use it is when something special happens. This lumped heat capacity model can be used when a dimensionless parameter called the Biot number defined as H LC over K is less than 1/10. If that's satisfied, we can take the easy way out and model the problem as a lumped heat capacity model. What is L sub C? L sub C is called a characteristic length. It's the volume of the object divided by its surface area, the area touching the fluid cooling the object. So there's some simple geometries. We'll put those geometries up on the board here. The first one is a plane wall. Okay, plane wall. This particular plane wall has convection on both sides. The wall is 2L thick. X is measured from the center line of the wall. On both sides of the wall, we have convection to a fluid at T infinity. With a convection coefficient of H. L sub C is equal to L, okay. It's called the half thickness. Another common geometry is a cylinder. Whose radius is R naught. Again, it has a fluid blowing over it at T infinity with a convection coefficient of H on the surface. For this case, L sub C equal the radius divided by 2. Now we have a sphere. Again, we have a fluid blowing over the sphere at temperature T infinity with a convection coefficient H on the surface of the sphere. L sub C equal R naught over 3. So those are three common geometries that we engineers study. I'll tell you later on give you some idea what they really could be. But for right now, plane wall, a cylinder, and a sphere. BO number, HLC over K. Here's LC. I don't care what the object is, you can find LC for it. For instance, what if I had a cube of aluminum? Cube of aluminum. Each side, A. L sub C. Volume over surface area. Volume, A cubed. How many sides? 6. What's one side? A squared. L sub C, length of one side divided by 6. That's what goes in the BO number. So for any object, it's the volume divided by the surface area touching the fluid. All right, well, that's kind of half the story. We know the full story. The full story is once we get the temperature of an object, whether it's temperature is a function of the geometry or of time, the second thing is find out something about how much heat transfer has occurred by convection or how much energy the body has lost by convection. So now we want to find the energy lost by the body. And how's that energy lost by the body? Well, convection to the fluid takes it out. Now, it could be the reverse. Hot gas, initial temperature low. You heat the body. Doesn't matter either way. All right, so Q equal integral 0 to time T. Rho HAS, pardon me. HAS, and then we have our theta d time. Convection by convection. Here's convection, Newton's law. HA delta T. Theta is delta T. T minus T infinity. dt, time, integrate, with respect to time. Where you see theta in here, put the boxed equation right there. Put that right there into there and integrate the exponential function. Just so you know, the Newton's law, HA delta T, is in watts. A watt is a joule per second. What's this guy here? Seconds. When I multiply joules per second times seconds, I get joules. Capital Q is joules. Little q is watts. Q in joules is energy, and of course watts is the heat transfer, the power, watts. So now we've got two Q's, a capital Q and a lowercase q. You talk about energy, you talk about capital Q. You talk about heat transfer, you talk about little q. Okay, put those guys in there, do the integration. I get Q So there are the two equations that we need to solve. Okay, so let's see what I got here. Any questions on that before we go on then? Okay. Well, let me think here. Oh, here it is. All right, so we're going to then take an example. The example that I'm going to work is a copper sphere. Let's put that on the middle here. So we're going to look at a copper sphere being cooled by air. I might need him. I'll leave him up here. Diameter is 15 centimeters. Yep. Initial temperature 300. Air temperature T infinity 30 degrees C. Properties at T average. T average, you don't want to take the properties at the starting temperature. You don't know what the final temperature is. So probably your best guess is to take the properties at the starting average the average temperature, starting temperature plus air temperature. And once you solve the problem, go back and put the right final temperature in there. I want to know the temperature, how the temperature varies with time. So find T as a function of time. I'll put the properties down for copper. Okay, step 1, chapter 5. Check BO. Maybe you get lucky and the BO is less than 1/10, and you can use this model, the simple model. Okay, BO equal HLC over K. H 25, K 393. L sub C from the table, geometry, a sphere, L sub C, 1/3 the radius 7.5. .20159, which is a lot less than 1/10, so we can use lump T capacity. Okay, first decision done. I get the easy way out this time. Here's the equation in the box. There's the equation. Okay. If I want to find the time constant tau, my time constant rho c h over h r naught over 3 L sub c v over as is L sub c. Okay, put those numbers in there. I get 35, 46 seconds. Time constant's almost an hour. It's cooling really slow. So then I know everything here. The properties, I know H, I know T infinity, I know Ti. So T as a function of T, then when you put the numbers in, T, put T in seconds, and the time will come out to be degrees C. So that's my solution then. Now, if somebody asks me, oh, by the way, in the first 5 minutes, how much energy is lost by the copper sphere? I say, okay, here's over here. The first 5 minutes, 60 seconds per minute times 5, 300 for T. I know that, I know that, I know that, I know that. I know tau, I just found tau. Put it in here. So many joules of energy is how much energy the sphere has lost to the air. Now you say, well, how much heat transfer has occurred? How much energy has gone out by convection? It's the same answer. The change in internal energy is the same as the amount of energy lost by convection. It says it right here. Change in storage is the same as how much energy goes out of the body by convection. Okay. All right, any questions on that then? Okay. So now, of course, the obvious question is, yeah, but what if the BO is greater than 1/10? Okay, now we got much more difficulty mathematically. Yeah, that's going to be Monday. We'll save that for Monday, okay? All right, so I want to go over some things about the midterm on Friday with you, so let's do that right now. Any questions before I erase any of this? Yes?
Where did we get the 270?
Which one now? Here? Oh yeah, it's this guy here, 300 minus 30. All right, let's take a look then, a little bit of review, and it's going to be not in great detail, but just to kind of jog your memory of what could occur on the first midterm. So here we have chapter 1. Is Elizabeth here? Elizabeth? Okay, I got something up front here. We're done. A paper for you. Okay, let's take a look and see chapter 1, Fourier's law. Newton's law, convection. Fourier's law. Ka over L delta T. Newton's law, HAS delta T. Radiation. Small object in a large surroundings. Okay. Epsilon, sigma, A, T, object to the fourth, minus T, surroundings to the fourth. If there is, that's for a black body, epsilon is 1. Alpha, that's the emissivity, is 1. The absorptivity alpha, if you multiply like the solar input on the street out there times alpha of black asphalt, then that's how much is absorbed by the black asphalt. Alpha is the absorptivity. Epsilon is the emissivity. Then we had, like over here, energy balance on a control volume. Then we had a surface energy balance. And that gets us to chapter 2. Chapter 2, real short, but Chapter 2 starts out with the tables in the back. Just to become familiar with what's there for you. What was the solid? What was the liquid? What was the gas? At what temperature? All that stuff is in the tables. And then, heat diffusion equation. Different versions. The rectangular version, okay, there's one of them right there. That's the heat diffusion equation for constant properties, no generation. So obviously that should be on your equation sheets. Rectangular, cylindrical, spherical. 3 equations. Know how to specify initial conditions and boundary conditions to apply to the partial or ordinary differential equation. Okay, that's chapter 2. Let's go to chapter 3. Okay, chapter 3 is our resistances. Yeah. All right, we have conduction resistances. Again, we have plain wall, cylindrical, spherical, and we have contact resistance. We can, then we have convection resistance. Then we put these in series, parallel, series parallel, or others. We had a problem where the heat input from a chip came into a certain point and it split, and some went down and some went up. So that's neither of these 3. So there's other geometries that you construct these circuits. Okay, okay. Fins. Possibly use table 3-4. Fins of a uniform cross-section area. They give you QF, and it gives you the temperature of the fin as a function of X. Maybe you can use table 3-5. Table 3-5 gives you fin efficiency, and then use that to get QF. But maybe you can use figure 319, or maybe figure 320. They give you A to F and put it in that equation to get QF. And then maybe you have multiple fins on a surface. We had problems like that. Okay. Now we have chapter 4 then. Chapter 4, draw a flux plot. Show the adiabats and the isotherms. Find capital S. Capital S. Conduction shape factor. Use it to solve for heat transfer. Okay, if you want a resistance, the resistance is 1 over SK. And you can combine that resistance with other resistances, like the convection resistance, 1 over HAS. By the way, this conduction shape factor, then you use Q equal SK delta T. That's how you put Q in there, or S in there to get Q. Now, the last half of chapter 4, numerical methods, will not be on the midterm. So stop there after the conduction shape factor, capital S. Okay, now let's talk about maybe what you should look at as far as example problems in the textbook. Of course, you know, I told you before, anything I boxed in the lecture probably should be on your equation sheet, because I think it's an important equation. But beyond that, there may be equations or whatever you use to solve homework. If that's important, you put that on your equation sheet. Not just what I box in class, but what you use to solve homework problems. So here are example problems in the text. It depends what textbook you're looking at. If it's the heat transfer textbook, Introduction to Heat Transfer, it's going to be the left-hand side. If it's the heat and mass transfer textbook, it might be slightly different. So these are the example problems worked in the chapters in the textbook that I think probably are important for you to look at before the first midterm. Chapter 1. Chapter 2. Chapter 3. Chapter 4. Now these same problems are in the heat and mass transfer textbook, but sometimes the numbers change because the author changed the textbook slightly. So these are the ones that are similar to the left-hand column, but they're in the heat and mass transfer textbook. It depends which one you've got in your hands or on your laptop. Most are the same numbers, but there's a couple that are slightly different. Got it. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 4, 7, 9, 1, 3, 4, right. 1, 2, 3, 6, 6, there should be, okay. I thought I missed one. 6, 9, 10, 4, 1, 3, 9, 3, 10, 4, 1. Okay, 15 in-chapter worked examples. You've worked 18 homework problems. I've worked 21 problems worked in class. You got 6 previous exam problems. So you've got a library now of 60 problems you can review for the first midterm. 60 problems for the first midterm. So that's what you, if you want to look at stuff, that's what you look at right there, okay? What's most important? Well, obviously, what I asked for the last 2 years, that's that one. When I assign homework, why do I assign certain problems? Because I think they tell a really good story. That's the next important one. When I work in class, because I want to go over that with you to see if you can understand what I'm doing up here in the board in class. This one here, this is the one, this is working class. This in chapter 1, that's what the textbook author thinks are important. Okay, that's all right, but that's not number 1 on the list. This is number 1, this is number 2, this is number 3, and that's number 4, if you've got prioritize your time for looking at stuff. That's what I would suggest. Okay, any questions on that then? Okay, you know what you can bring to the test on Friday, what I'm going to give you on Friday. So we'll see you on Friday then. If you have any questions, hang on around after class. I'll talk to you about any questions you have.